Welcome back. Today we're going to talk about energy conservation, part 2. More exciting than part 1, because in part 2 we're dealing with non-isolated systems. We're kicking off those training wheels. So now we're going to be able to change the total energy of the system through this quantity we call work. Couple important notes. If your work is positive, you're adding energy to the system, whereas your work is negative, you're taking energy out of the system. Let's look at an example. So here we've got this block. The block is being pushed. All right? If we're pushing, are we adding energy or taking energy out? All right, well, let's see. We're increasing the speed, so we're looking at delta K. That's the only type of energy we've got right now, which equals work. Sometimes this is called work energy theorem, but we're going to use this as a special case. So moving on, we know our initial velocity, final velocity, just our expressions for kinetic energy. We'll plug in these numbers to get a quantity, and lo and behold, our energy is positive. Why? Because energy is going in. Energy is being added by whatever is pushing. So now we're going to have this block. It's already moving. It's going, and then it's going to come to a stop with friction. So the speed of the block is decreasing. Is energy going in or out? All right, well, let's find out. So again, we're only looking at the kinetic energy equaling to the work. We'll plug in our values. Again, final, it's going slower now, so our final, which means, wait a minute, this number is going to be smaller, so our work is negative. It lost energy. Oh, let that be a lesson, that friction is always negative. The work done by friction is always negative. Friction takes energy out of the system. You never said, oh, need more friction, that way it'll speed up. It doesn't happen. It doesn't make sense. One more example. This one's a little bit different because here we're looking at friction, so we know the work's going to be negative, but we're given a rate. We're given it 4 joules per meter. Oh, but we need the work, the energy, the unit of work is the joule. So I know that if I've got joule per meter, I need something. What do I need? I need another meter to cancel so that these units make sense. So this is actually going to wind up looking like work here is going to be some rate times delta x. This part over here is just your standard kinetic energy. We've seen that before. But here's the rate. This is the rate per meter, and then this is in meters. So our units work out nice. Notice this rate is negative because friction always does negative work. And then when we plug in, we get delta x is equal to 20 meters per second. So it takes 20 meters for this block to slow down due to friction. As a final recap, the main difference in this chapter is that now your change of energy is not zero. When you're talking non-isolated, you get this work term. Something's adding or taking energy away. Hope this helps, and I will see you in class.